Once you have a state machine that defines how you want your system to behave, you build the code to match the picture. If you need a reminder about what a state machine is, click the link above. For object-oriented languages, there's a standard pattern for how we build the code to match the picture. But I want to show you a table-driven solution. I'll show you how to build it in object-oriented languages and in C. I strongly prefer this solution to this standard pattern, and I'll explain why. First, we need an example to show how this works. This is a simple machine for a traffic light. It just cycles from red to green to yellow and back based on timers. Let's make it a little more interesting. When an emergency vehicle is racing to help someone, they have the ability to preempt traffic lights to make their side green and the other side red. If you think about just a light that is supposed to go red when it's preempted, you might make a machine like this. Our general strategy is to make everyone go red on preemption, assuming that the other direction of the intersection is going to go green for the emergency vehicle to be able to pass. Then, when the preemption is over, the people who had been stopped at the preemption are allowed to go, and the people who had been going at the preemption have to wait. This is the preemption path for people who are sitting at a red light when the preemption starts. When it ends, they get to go. This path is the preemption path if the light was green when the preemption happened. This example is good enough to show how we code a state machine, but certainly not realistic. You wouldn't manage one light independently from the rest of the lights in the intersection. The table-driven implementation of a state machine is grounded in the way computer science theory codes state machines. They describe the edges of a graph like this. Each edge is defined by a source state, the input that initiates the transition, the action attached to the transition, and the state the transition moves to. The whole machine can be described as a table of the edges. Given that table, the code that runs our machine processes an input by searching the table for a row that matches the current state and the input received. From that row, it knows what action to take and what state to move to. That description is the pseudocode for the solution. Let's look at some of the details. The states in that table are a finite, discrete set of values, so they're usually implemented as an enum. Well, that was easy. Next, let's talk about the actions. We need to be able to build a piece of code that completes the action, and then put that code into the table. If we're in an object-oriented language, we essentially need the strategy pattern to put a different behavior in each row of the table. So we need an interface that all behaviors will implement, and a concrete implementation of that interface for each behavior we need to code. For this machine, that would look something like this. And the rows of our table would code the creation of the objects for each behavior. If we're building that in C, we code those behaviors in functions and put function pointers into our table. If you need a root view of how to do that, check out the video above. The last thing we have to worry about is how to encode the input required for each transition. Well, that depends on what kind of inputs you get. Suppose you're building a game where WSD and space are your inputs. Well, then we could just code that column of the table to be a character. For this machine, every one of these things is an event. If we can make a list of those events, those values are what goes into the table. So this one's pretty easy. Let's look at a different machine where things aren't so simple. Even in situations like this machine, which I covered in the previous video, where all of the inputs are characters, if we had to encode each character, an edge like this would have had to be encoded as 10 rows in our table, one for each digit. Well, that's pretty messy. When we can't directly encode the input, we build things that check if an input meets the criteria an edge needs. This is exactly like encoding the action, a strategy pattern of behaviors implementing the behaviors that check if an input meets a criteria and objects of those behaviors in the table, or a set of functions with function pointers in the table. For completeness, let's look at the code that uses these tables. To start, we need a variable that holds the current state, and we initialize it to be the machine's start state. which in this case is the red state. Every time we get an input, this method gets called, passing in the input, which for us tells us which type of event occurred. The code searches the table for a row whose source state matches the current state and whose input requirements match the current input. If it gets all the way through the table and didn't find a match, it outputs an error and returns. But if it found the edge, it executes the action attached to that edge and makes the current state the state that the edge points to. That's the general strategy for how these machines work, but you can customize this strategy for your specific situation. For example, in this machine, every edge does two things: changes the state of the light and possibly sets a timer. Instead of putting those things into one action, I think the table is clearer if we make each edge have a light action and a timer action. That way, it's really easy to see that the code matches the picture, and it's easy to understand the behavior of the machine by looking at the table. There was one other clue that implied that we needed to do this. In the original table, we had to pass an instance of the machine into each action. That was there so that the actions could start the machine's timer. That bidirectional coupling is really unpleasant. By separating the timer behavior from the changing of the light, we've eliminated the need for the actions to have access to the machine. Bidirectional coupling removed. Given this standard design pattern for implementing state machines, why do I like this? Well, the standard pattern builds one class for each state. For a Moore machine, where the actions happen in the states, that might make sense. However, much of what we are coding in the state machine diagram is how we transition between states. My concern with the standard state pattern is that it's really hard to check that the code matches the diagram. The transitions out of each state are coded inside those state classes, so the motion of the machine is scattered across the state classes. When we code the machine in the table, it's really easy to compare the table to the diagram and make sure they match. And if we change the diagram, we just have to change the table to match. For me, that makes this implementation robust to design changes, and that's a big selling point.